Hello everyone, we are Team SmartFEP from Huazhong University of Science and Technology in Wuhan, China. It's a great honor to have the opportunity to share our work here. The outline of this report is as follows. The content of this competition can be divided into two parts, partitioning and placement. For the former one, the optimization goal is to improve the resolution accuracy, but because its constraints are very tight, it's necessary to carefully consider the feasibility of the solution while optimizing. For the latter one, the wire length evaluation of 1.5 norm requires the optimization of this solution to maintain the overall cost balance. Both of these problems are large-scale NP-hard problems. It is very important to improve the search efficiency while optimizing the objective function. For partitioning, we adopt a bottom-up design approach. We first determine a feasible inverse sample step to partition the original space, and each PE covers an area with the highest resolution. In this case, we can get an initial solution with an overshoot of 0. Since the total number of PEs required for the initial solution may exceed the limit, the second part merges the appropriate tiles to reduce the total number of PEs used. In addition, the accuracy of a single tile can be improved by merging while ensuring the overshoot is 0. After processing all mergeable tiles, if there are surplus PEs, we try to split the tiles. This operation can not only reduce the overshoot, but can also improve the score of the corresponding covered area. In addition to the above two operations, we also have made some detailed optimizations. First, if there are a lot of empty locations in the original space, we merge these areas first to optimize the memory. Second, we try to reclaim the wasted PE, that is, those PEs that covers the empty area. In addition, when the optimal solution is reached or no feasible solution can be found under a certain inverse sample step, we can carefully improve the inverse sample step to relax the restrictions of max scale, and alternatively perform merge and split operations to try to get a better solution. For the placement problem in the second part, we use a heuristic algorithm for optimization. The initial solution is constructed by performing best first search on the three-dimensional space and greedily constructing on the two-dimensional plane according to the cost of wire length. Then we use the variable neighborhood search and taboo strategies to optimize the initial solution and gradually get a better solution. The three search neighborhoods are briefly introduced below. The first neighborhood move is to grab adjacent tiles. As shown in the figure below, when a PE's neighbors are far away from its wire length cost, and its wire length cost is high, the PE pulls all its neighbors closer. At the same time, in order to prevent the operation from disturbing the whole structure, we only move the adjacent tiles to the area in the middle of them. The second neighborhood is to get close to the adjacent tiles. When the distance and cost between neighbors are small, we consider moving the current tile towards its adjacent tiles. For the same reason above, we only move to the middle area. The third neighborhood is to look for improved exchanges around. When the cost among a tile and its neighbors is small, it's only need to look for improving moves around. Apparently, this neighborhood structure is smaller, thus being more efficient. Here we show the optimization results of a public benchmark instance. In this dataset, we used almost all available PEs and used most of the PEs for calculations instead of as adapters. From the final results, we reached a full score in the wire length optimization, and the result of the partitioning part is also good. Finally, we thank the organizers for providing such a platform to tackle these two interesting and challenging NP-hard problems. We hope to learn more excellent methods from other teams. Thank you for listening.